Okay, we're good. All right, in this first question, we are going to, since we have a understanding of how trusses work, or what the definition of trusses are, we are going to solve for this question over here, where we have an example of a truss, and this truss has three members, right, which we've drawn over here in our example, where we have 1, 2, 3 members. We have some distances. The bottom member seems to be 6 meters long, and then the two members go up to 5 meters in the air. We have our two supports. Now, in our example question, we have a fixed support on both sides, left and right, but for us to solve this question, we have to simulate one of those as a rolling support. And in our notes over here, we said if we do not have a rolling support, we'll assume that the rightmost or the lowest support is a rolling support. So that's why I've defined this one over here as our rolling support. We have a force of 5 kilonewtons going down from the top. Next thing I'm going to do in this question is I'm going to start to label some of these members. So I'm going to label the nodes, which in the nodes in this example is everywhere where two or more members are connected together. We have one member over here, another member over here, so this over here is a node, and we will call this node A. Over here, we have two members connected together, so we will call this node B. And we have a third, let me do that larger so you can see it. And up here, we have two members connected together, and we will call this node C. Also, we know that whenever we have an external force or a support, they have to be applied to nodes. And if we check our scenario over here, this checks out. We have a vertical force, so a vertical external force over here, which is connected at node C. So that is correct. We have our two supports over here for one's at node A and the other one is at node B. So the first thing we are going to do when we want to solve a truss analysis question is we have to do all the work we did from our last lesson, where we have to solve for our reaction forces. So just a reminder, those 6 steps is we're going to simplify our supports, which we've already done in this scenario. We have to identify the reaction forces. Then we have to define equilibrium, identify and simplify the loads, which we've already done. Then do our sum of all moments to find out our reaction forces. So let's do we've already done the first step where we've said rolling and pin. Now let's just draw, and I'm going to draw in green for where my reaction forces are. B is, the rolling support on B can only be vertical. So it's going to go over here and draw a arrow going up. This over here, and we can call this force reaction B vertical. And for our A, it is a pin joint, so we can have a force in the vertical and in the vertical and in the horizontal. So let's just pick the direction. Let's just pick that direction for now. And remember from our last examples, if we got a negative answer, we just know that that means our initial assumption of the direction was incorrect. So, and I'm going to call this reaction A vertical and reaction A horizontal. Okay, now we're just going to simplify using our sum of all forces. We know the system is in equilibrium, so I'm just going to write these up here. Sum of all forces vertical equals 0, sum of all forces horizontal equals 0, and sum of all moments equals 0. Our three equations that are true for a system that is in equilibrium. So our first step for solving this is we are going to do sum of all moments around the pin support, which in this case is point A, where clockwise is positive, equals 0. This means that we have this 5 kilonewton force over here. Now if we measure the perpendicular distance of this, if we measure the perpendicular distance, it's going to be this distance over here, which is 3 meters. This is the perpendicular distance of that force. So that will be 3 times 5 kilonewtons, and it is going to go in the clockwise direction, so it's positive. Then we have over here, we have our reaction force RB. This is going to be 6 meters, so 6 times whatever RBV is, and this, if we're assuming this arrow is going up, this is going to be counterclockwise, so it's going to be negative. Then we'll get RBV should equal 3 times 5 kilonewtons divided by 6, and if all is correct, that should be a bit of a fraction. Sorry, let me get my calculator. That should be 3 times 5 over 6, and that should be 2.5. Alright, so that's going to be 2.5 kilonewtons, and its direction is going up, so we already know that, so we can write this over here, so we can say equals 2.5. Right, now we can do our next thing, which is our sum of all forces vertical, where up is equal positive equals 0. We have RAV, we have minus 5 kilonewtons plus 2.5 kilonewtons. So then RAV is going to equal 2.5 kilonewtons up. Alright, so that means we have 2.5. And the last one we have is we have sum of all forces horizontal, where we can say going to the right is 0. We have RAH, and we have nothing else. This over here only has a vertical component, so RAH is going to equal 0. Ooh, my pen. We know that this is going to equal 0. Alright, so we've found our support. So now, so far so good. We've already done this before in class. Now, we are going to we have to find the forces on these members. So what we are going to do is we are going to zoom in to a particular portion of this scenario. We are going to zoom in to, let's zoom into this part over here that I've highlighted. Right, we are zooming into this node over here. Right, we can call this the yellow part. So let's zoom in on this particular node over here. And so I'm just going to see the forces that are on here. So we have a node. We have a member going out this way. We have a member going off at this particular angle, which is, I know it's a difficult angle to find out, but it's, what is it? It's 5. It's like 5 and 3, right? It's a weird angle, but it's coming out there. And let's look at what we have. We have over here, we have a force going in at 2.5 kilonewtons. We don't know the amount of force that's coming out of these two pins here. But what we do know is their direction, right? So we know over here, we have either a tension or a compression, and we know that its direction, I'm going to draw it in pencil because I'll change the color once we know what it is. We have either a force in tension or compression going in this direction. Same with this top member over here. We have a force going in tension or compression in one of those two directions. So what we can do is, when we solve these questions, we are going to assume one of these. Or we're going to assume whether a member is in tension or compression. And just like with our previous part with the reactions, if we are incorrect, we just got to reverse our assumption. So let's say over here, this is going up, this is 2.5. Let's just say that this particular member is going to be in compression. So let's just get a red arrow going down. And let's just say this particular one over here is going to be in tension. So we'll get a green arrow going to the left. All right, so I've just defined the forces going in that direction. So now in this particular scenario over here, and I believe one of my students has given me the angle over here, which is 59. I'm not going to round it up to 59 degrees. So we have here we have the angle. So we can, in this scenario, we know this system is under equilibrium, which means the whole system is under equilibrium, but also this individual scenario over here is under equilibrium as well. So we can go and do our equations again. We can say sum of all forces vertical equals 0. Sum of all forces horizontal equals 0. There's not going to be any moments around here, so we don't have to worry about writing the moments down. So let's break down this particular force over here into horizontal and vertical components. We have, and this force over here is going to be force BC. If force BC is coming down, like if this is over here, this is force BC, and it's going to be at 59 degrees, then this part of the force over here will be this part should be cos 59 times force BC, and this over here should be, this is going to be our horizontal portion, and our vertical should be sine 59 times force BC. Yes. So what we've done is we've broken down, we just wanted to break down this particular angled force into horizontal and vertical components. So let's now write out these equations here. We have sum of all forces vertical equals 0. Let's get all the vertical forces in this scenario over here. We have a plus 2.5 kilonewtons. We have a minus whatever the vertical component of this angled force is. And our vertical component is sine 59 times force BC. So if we go sine 59 times force BC, if we then go and simplify that, we have force BC equals 2.5 divided by sine 59. If we put that into the calculator, we should have 2.5 over sine should get us it's going to equal 2.9 equals. So what we've done here is we've identified that the force is going to equal 2.9, and we're all in kilonewtons. So our force is equal to 2.9 kilonewtons. Two things that we note from this. One, we found out the force BC, not the angled force. So this is the this force, not the horizontal and vertical. And secondly, our answer is positive. So our original assumption that it was going down to the right was correct. So we have found this over here. We can say this force is over here is going to equal 2.9 kilonewtons. Okay, now let's go through the next scenario where we do sum of all forces horizontal equals 0 equals. So now we want to do all our horizontal forces. Well, this has nothing in the horizontal. We have this over here, and I believe this is force AB. Fab. And we are going to say minus FAB plus, well, we're going to want to do this horizontal force over here, which is cos 59 degrees times, well, we already have our force BC, so times 2.9. And then our FAB, if we just do that equation, should be cos 59 times 2.9. And that should give us an answer of 1.49 kilonewtons. All right, and again, the answer is positive, so our direction was correct. So what we've done here is we have already started to identify we've already solved two members of this equation, of this scenario. We have solved AB and we have solved BC. If we write this over here, we can say that BC is going to be 2.9 kilonewtons, and we're going to say C to denote compression. And over here we can say, oh, I've been doing it wrong. Green isn't tension, it's blue. My bad. Pretend fab is in blue. And then over here we have 1.49 kilonewtons in tension. So that's what the T is for. Hopefully you can see that 1.49. Alright, so we can do this same approach. We can do this for the other side, because we can just continue our equation. Or, this is boring, this side over here, because it's going to be exactly the same as this one. So how about for this scenario instead, I show you the top. I'll show you this one over here. So I'm going to have to go onto a new page, but all we need to know is our trigonometry. So we'll add that in. In this scenario over here, we have a node over here. We have a 5 kilonewton force. We have, and we have two members coming out like this. And we already know, so again, we know the angle of these. We know that this angle over here is going to be 59. And we know this angle over here is going to be 59 because that's what the geometry of the scenario is. We know that this is under compression. So if we look at our scenario over here, where our compression was pushing, it's heading towards the node. If this member over here is also under compression, it is also pushing towards the node. So this is a key thing that we've learned here, or that I'm telling you. The direction has technically changed. This over here is going to the down, and this is going down and right. This is going up and left. But that is because this is the same member that we had before, and it's just experiencing the forces from like that. So it is going towards this node. And we know that this value over here is 2.9. And we've already assisted ourselves because we already know our equations over here. We already know it's going to be, for this over here, horizontal. For its horizontal, it's going to be cos 59 times FBC. And vertical is going to be sine 59 times FBC. So we know that we already have those equations, so we don't have to do those twice. All right, so let's do, and this over here is also going to be the same. We don't know the direction that this force is going in, but for this example, I would like to show you something called smart guessing, all right, quick maths. We know over here that this over here is a force that is going down, and we know that in our equation we are going to, at some point, have to deal with sum of all forces vertical, sum of all forces horizontal equals 0. Right, that's because we're dealing with equilibrium. We know that this is going down, and so we're going to have a force that goes up, and we already have a force that goes up, so we don't know if this over here is, we don't know if this over here is going to be going up or down, because mathematically it can still work out. But when we look at our sum of all forces horizontal, this over here has no horizontal component. So it's not going to be contributing to the horizontal at all. While this over here has a horizontal component, it is going to the left. So if this has a force that is going to the left, this force over here, due to this member, has to be the opposite of the left in order for us to get to 0. right? So this one has to go towards the right. So we know at some point this force is going towards the right. And then if we look at this member over here, the way it's angled, the only way this force can go to the right is if it's also going up. So it's going to end up being a force going in this direction. So we can use some of our geometry to our advantage to solve these particular questions. One of my students is asking, why do we know that this is an isosceles triangle? Because the question says it, because it's 3 meters down the bottom and it has a little mark in the bottom, which means that this part over here is in the middle. So this is going to be a 6, 3, 3, and 5 high triangle. So it's because it has that little mark down there at the bottom, is showing that that's like a midpoint, is where the 5 kilonewton force is going through. Alright, so let's solve this question. We are going to... Some of you that are going ahead and already thinking that, yes, it's going to be exactly the same, but I want to show it mathematically. This force over here, this is going to be force... If we want to do our horizontal and vertical for this one, its angles are the same, so it's going to be cos 59, but this is going to be force AC, because A is, this is going to be C and A is somewhere over here. So force AC, and this will be sine 59 force AC. So when we do our sum of all forces, we can do a sum of all forces vertical equals 0 equals, we have minus 5 kilonewtons. Then we have plus this vertical force, which is sine 59 times 2.9, and then we have this one over here, which is also plus sine 59 times FAC. FAC should equal I'll do it slower, equals 5 kilonewtons minus sine 59 times 2.9 divided by sine 59. If we do this over here, we should get 5 minus sine 59 times 2.9 over sine 59. Ah, yes, we get 2.9. Lovely. It should equal 2.9. So we have found force AC. We don't have to also solve sum of all forces horizontal, because all our questions are asking is to find the force in all our members, and we have found that now because we have FAC is 2.9. Give me another color to highlight our answers. We have determined that we have FBV over here. Oh my god, this is a terrible highlighter. We have FAB over here. Then we have FAC over here. Its direction is, it is in compression. So, and I should have written these over all. This is in compression and this is in tension. And then we can draw it over here. We can say 2.9 kilonewtons in compression. And so that is how we solve those questions. And if we look at the examples and the answers, if we look over here, these are answers that are popping up. And over here we see that 2.9, they use negative to determine. They use negatives to determine compression. So over here we have negative 2.9, negative 2.9, and we have 1.5, which is very close to our 1.49. And that's the correct answer we have there in the simulation. And that's, depending on what the question asks, you can put that into a table, but that is how we solve truss analysis on a simple question of a triangle.